Okay, let's start. Reminder for next time, again, that's going to be the presentation day. So make sure if you're presenting to send stuff to me. Actually, those of you who are presenting, if you can just drop me an email saying you're still in the class and presenting, that would be great, because otherwise I'm left wondering. So that would be nice. Okay, in any event, so last time I'd started on things that hardware can do to or does to help on the security front. And the first concept we had covered was, first thing we had covered was that how random number generation is assisted by hardware. You can do random number generation without any hardware assist, as long as you have some source of entropy, key presses or some sort of external interaction. But circuits which make use of noise and then convert them into bits that then you can either use as they are, or use as seeds into some secure random number generator, provide kind of the abstraction. And I mentioned that how in operating systems you so in Linux you see these things as dev random, which is directly connecting you to the source of randomness that the system is relying on, and dev urandom, which is basically unlimited randomness, and that is basically using that hardware provided entropy to then amplify it algorithmically. The former can block if the system has run out of randomness, so to say, and the latter kind of goes on forever. And then I had also talked about, so modern processors have some of these things built in, embedded processors don't, but then you can always add as add-on random number generators. So there are sort of little boards you can plug into Arduinos and Raspberry Pis and all, as well as sort of bigger boxes you can buy and hook them up through USB or serial port or things like that. Okay. The other thing that we had started on was the whole trusted processing module and secure enclaves and trusted execution environment, which are basically sort of various forms of you can say crypto coprocessors, which provide a grab bag of things, including secure storage of information, time that doesn't go backward, sort of generation of keys and things like that. And then the other thing is that they provide an ability to execute code and keep and manipulate data while maintaining secrecy even from an evil operating system. So kind of the motivation has been that we want to reduce the what all parties we need to trust in order to have trusted computing. So Intel's SGX is an example of such a concept, and the idea being that this anticipates that the operating system has been compromised, either because it was to begin with under the control of some third party, or alternatively it had some bug which some malicious operating system, malicious app exploited, and then the OS got compromised. So what this secure enclave in case of SGX does, it provides this abstraction that through some instructions you can create an enclave, which is nothing but a bundle of data and code which are encrypted in the memory so that even the OS cannot look at it, but whose integrity you can verify by some means that the hardware manufacturer provides, and I'm going to show that very shortly. In essence, this provides a level of privilege in the hardware which exists even more at a more privileged level than even the operating system. And in case of Intel processors, they implement it via microcode to provide this concept of enclave. And in particular, there is a one enclave that Intel provides, which is, think of it like the system enclave. And some of the services that application created enclaves depend upon require talking to that system enclave. the operating system can stop you from communicating, but it cannot tamper with that communication. When I say stop you from communicating, operating system does scheduling of processes, so it can always not schedule something. So that kind of denial of service opportunity is always there. So essentially, app in these systems are built using this kind of a split personality. There is a trusted part, untrusted part. When the system starts out using APIs that you are provided, basically you create an enclave, you verify that the enclave, the code inside the enclave and all is correct, that is operating system hasn't already tampered with it, so that you do with some lower level functionality provided, which essentially results in testing you are on the right, correct, whatever, genuine Intel processor, your code is fine and all. And then eventually your untrusted part interacts with the trusted part through specific function calls. So think of it like just like operating system, you interact with it through system calls. In this case, there are entry functions which the enclave provides, and you can only talk through that. And everything inside the enclave, which basically means all the memory pages and all, are all encrypted. Okay. So that's kind of the basic concept. So inside the enclave, you have a code and data which remain secret and which you have verified have not been tampered with by the OS, and where you have some very specific entry points. So you can't just call arbitrary internal functions in that piece of code. You can enter only but other than that, inside the enclave, you run in native speed. You can have multiple threads and all. You have full access to the memory outside the enclave, but of course, in that case, you are not assured its integrity. So the enclave itself is limited in memory size in case of STX. So, what it allows are things like, so let's say you have the enclave code running out here, goes over the bus, and if you go to examine the database on the bus, you'll see gibberish, okay, because the encryption is being done at the hardware level, so it's not as if you need any support at the board. Do you think in something like this, is there still any information leakage? So from the process running, and what we have made sure is every time it accesses the memory, the data are encrypted. Okay, so read, write are encrypted. But this is obviously going over the motherboard, because in our systems, eventually, I mean, of course, internally you're writing to a cache, and then the cache lines are being read written over the memory, except that they are encrypted. So my question is, do you see any possibilities of any security risks that an adversary who is basically able to tap onto these memory lines can cause?
Can they man in the middle attack? I mean, that adversary can
man in the middle attack is a little bit harder to mount, because you have to cut the traces and put something. You could think even simpler. You just you're able to monitor it. That's super easy to do, right? I mean, so you are obviously seeing encrypted data, right? But what else are you seeing? You're seeing addresses which are unencrypted, right? Otherwise the memory won't understand it, right? Secondly, you're seeing when the transactions are being done, right? Okay, so do you think, what can you, as an attacker, can you make use of that? Is there some information leakage there?
Periodic, we can estimate what is it trying to do, or maybe because like somehow if we know the computation time.
Yeah. So for example, let's say there was some sort of time series or image or something like that, and you're only going to touch pixels which were met certain criteria. So now you can easily say, how much data was being touched, or actually even which data was being touched, because you can look at the addresses, right? In case of a timing-oriented real-time type application, when does it happen, right? So actually this information that you still have can be used to break into things. So I think one of the papers I think for next Tuesday that I've done is work out of Berkeley where they actually show that how you can extract information from examining at this level, even though things are encrypted. Now there's an additional confounder out here, which is the processor, when it makes a transaction, it doesn't go to the system memory straight away, right? I mean, there are L1, maybe L2 and L3 caches sitting out here. So it's not as if the moment the program makes a transaction, there's a transaction out here. It's being kind of filtered to the caching mechanism. So you have a harder inference problem, right? Because you're kind of examining the actual transactions made by the process through this filter, think of it like a low-pass filter that the cache in effect is creating. And yet, you can still infer stuff. So what I wanted to kind of convey out here is that just because we have this whole encryption mechanism and all, it doesn't mean we have sort of closed all these things. So you could imagine that, again, remember one of the attack scenario was this Amazon or one of the cloud service providers mounting such an attack. Well, guess what? It's their board. They could have certainly put some sort of a snooper out there and kind of make use of that data as well. So risks still remain. Sort of these SDX is not the panacea. Yeah.
Is the encryption that we do always different for each process?
Oh yeah. So firstly, it's just AES encryption because that's what initial processors come with. So always different, as in the keys are generated for that specific thing. So it's so you encode the same byte again within the same process, whatever same thing again, it would be different every time. If you were to recreate the same enclave again, it would be differently encrypted. Yeah, that would be almost like if a system were to not do it, it's thoroughly broken. Okay, go back to the crypto lectures. Never ever use the key again. Right. So yeah. So absolutely. So those, I mean, these are professionally designed systems, designed by Intel. Okay, so it's not. Yeah. So those trivial, whatever, first order things are taken care of. So the crypto is strong to the best of whatever current understanding. Okay.
Because the OS can always, like, has the key always away.
No, the OS does not have the key.
Yeah, but if the OS tries to create the enclave,
the enclave is created by the hardware. There are instructions to create enclave. It's not being done by the OS. Of course, it's through the OS, but the main thing is I have it on this slide. I think I may have later on, but there is a procedure out here where the enclave can, where you can check for the integrity of the enclave there. So, yeah. So, for example, let's say you have an app running on your embedded device. It's collected some sensor data. It wants to get it processed on a remote server. So on the remote server, it creates the app component running. There is some component inside the enclave and that remote. Your piece out here can verify that piece inside the enclave has not been tampered with. Remember, it's your app, right? So imagine an app on your Raspberry Pi. Okay, it sends some data in code to this remote server, and that code has two halves to it: a secure half and a normal half, right? And there, the unsecured half creates the enclave, so puts the data secure half there, and then this is the part which is now going to do the privacy sensitive stuff. Like, I'm going to send my encrypted sensor data to the stuff inside the enclave, and there it will decrypt, compute, send back the result to me. Okay. But before I do that, how do I know that the operating system didn't manipulate the code I sent to it? Right? So what I will do is intuitively, in a very handy fashion, I'll ask the stuff inside the enclave to, let's say, send me a hash of itself. Okay? And it's going to send it by encrypting it using, again, I'm just throwing a plausible scheme, it's not necessarily the way it works. It will encrypt it using my public key. Okay, so no one else can do it. I'll get it, and now I will verify that it is correct. Okay, and of course, sort of on the remote party. And in this case, actually, There is some additional stuff you can do where you can have it be signed by the hardware, so you can verify that it is actually a genuine hardware. So all those things are provided as part of this SGX capability. So the way, so client application, and there is a remote platform. The Enclave is built and then measured, and by measured is what I mean, that you kind of verify whatever. Let's say compute a hash over it or something, like you kind of verifies property. Let's see, and then you work together with this remote platform to kind of verify that things are okay, and there is Intel embeds keys into the microcode at the time each processor is built. So each processor is unique, and so you are able to verify things. This kind of, and then essentially what is happening is that you are establishing your the part which you are running on kind of the trusted platform is like in my example, let's say my phone or whatever Raspberry Pi is outsourcing computation, then I basically will have an encrypted channel to my code running inside the Enclave on that server, okay, or in this case the client app as is shown out here. So the OS on the potentially evil OS cannot do anything other than stop the communication. Okay, so that denial of service is still there, but it can't. Well, so it can do two things. It can deny service, and it can add delays. Okay, which is essentially generalization of deny service, but it can't tamper with the content, and it can't snoop at the content, and that's the assurance that Intel is providing. Modulo, like I said, there is still someone who's snooping the bus, some work is suggesting that you can still do things. There are also some work which have shown that so code running inside the SGX still makes use of the cache. And as we have seen with those meltdown and Spectre attacks, there are possibilities that cache also leaks things. So people have shown that even stuff running inside the enclaves can leak information if you're not careful about the side channels that do exist in these systems. Okay, so anyway, so there's a crypto protocol around this, which I'm just glossing over, which provides kind of which makes all of this kind of magic happens. Now, Intel SGX is probably the most well-known stuff, and its primary target is servers. Okay, so you find it started out with the Intel Xeon processors, and then is available on all things, even all Intel processors, even the Celeron and Atom type processors and all. But Intel processors are not very common on embedded devices. ARM processors are. So ARM has a different take on this issue of what should a secure enclave do. So the issue that the way ARM comes at it is the following, that problems occur when things are complex, and that's probably a fair statement in the sense that complicated things tend to have more undetected bugs and stuff like that. So what ARM does is that in their processors and their more advanced processors, so like A series, which is what you find in smartphones and all, or Raspberry Pi, not M series, which are kind of tinier one, although what I'm talking about has also begun to emerge in those microcontrollers. So it's something called trust zone, and kind of the idea is that it's almost like you have two processors, except that it's the same processor, and you switch back and forth between these two modes. So one is kind of this non-trusted mode, which is kind of the standard mode that exists in our processors, which in turn can have privilege levels and stuff like that. But then there is also a trusted mode, and the idea is that the non-trusted part doesn't have any access to the trusted part. It's all literally like you partition it off. Okay, so it's any accesses to that and all would not be allowed. So the way it works is that you can map regions of memory and regions of I/O space, like certain pins, like you can say serial port and all, is on the trusted side. And the idea would be that your normal OS and the apps on top of it, which are all running in the non-trusted side, will not be able to have access to those things. Inside in the trusted part, whatever is running has access to those. So you literally have kind of partitioned the processor into sort of these two halves. This is closer in spirit to the idea I was saying last time, that I can have two processors, a red processor and a black processor, okay? And I kind of literally kind of try to separate them out, except that the separation in this case is actually the same piece of hardware. So you could run an arbitrary OS as you normally do on the normal side, but then inside the trusted side, again, you can do the same thing. Now, one advantage of a couple of advantages of this approach that Arm took is that firstly, the memory size is unlimited. So I can, if I have, let's say, whatever, 8 gig of RAM, I can say 6 gig belong to trusted. Fine, okay. It will probably defeat the spirit behind this thing, because the idea is you should carve out the smaller critical part of your system, which you really thoroughly care about, and have that be on the trusted side. Because if you can in principle run the full-blown Linux or whatever out here, but then you have all the same issues that you were afraid of. So you run some carved out part out here, but at least there is no limit memory. The other thing is that the I/O pins can be mapped out here. So you can have trusted peripherals and all, which are only visible to the trusted side. In case of the Intel one, you don't have that possibility, because that Enclave in case of Intel is a purely execution, purely computation focus. So one place where I doubt any of you would have ever used it, but until not too long ago, Samsung's phones used to have something called Knox. Knox after Fort Knox, which is America's gold reserve. Okay, so essentially you could isolate some applications on those Samsung phones to run in that secure mode, and essentially they cannot be affected by normal apps in Android and all. Okay, for some, I guess there wasn't probably much demand for it, so I don't see that in the newer Samsung phones. But Samsung for a long while was chasing, like, US Army uses Android quite a bit, those kind of things. So they actually use Samsung Galaxy soldiers. If you see these soldiers with all sort of electronic gears and all, the phone on there, this thing is a Galaxy phone. So I think they were chasing that kind of hardened Android market quite a bit. So the idea, or if you're a company, maybe what you can have is inside that Knox would be your enterprise apps, which would then be able to talk to your company thing and all, and then sort of rest of your apps could be normal. So this model often is called as bring your own device model, which is you may want to have users carry one phone, they're installing their whatever social media apps and whatnot and all, and yet I can have certain apps which are kind of secured away in this thing. So that was sort of the model, but then inside this trusted part, you will have an OS, so there are lighter weight operating systems that have emerged for this purpose, and then the interaction between these two, switching back and forth and all, is managed by this part. So obviously the red part cannot call stuff in the green part, but the green part can switch over. One of the dings against this thing is that the switch over is expensive. You literally are kind of switching to a different operating system at that time. So the Intel one, you create the Enclave and then it's kind of like a function call. But here, switching back and forth is more expensive. So anyway, that's on Trust Zone, and like I said, at this point, so it's also available on those Cortex-M processors, at least some of them, some models of them, but the software support and all is not as great as if you're working on the A series thing. So if you want to use Trust Zone on like the Raspberry Pis type of things and all, it's very easily done. But again, one thing I would emphasize is that kind of the whole purpose gets defeated if you run complicated stuff inside the secure part, because then you're dealing with all the issues that come with that. And AMD has something similar. I don't recall the name, and RISC-V, which is The other embedded processor, which is getting a lot of traction, mostly because it's entirely open source. Also, people have created similar things out there. So it's a very active area of study, both in terms of trying to break into it as well as kind of other abstractions. Some of the things, for example, are currently not easy to do. Let's take the Intel platform. If you want to use a GPU, so a lot of times, I mean, I gave you this example. I'm sending the data to a cloud service, and I want to run a machine learning model. So how do I access the GPU from the code which is running inside the SGX? But I have to access the GPU. Now remember, on the Intel machines, I cannot have any sort of accelerator or GPU be hooked, be directly accessible from the SGX. You have to go through the operating system, in effect, the main processor. So that presents a challenge. You either need to have some sort of secure channel to your accelerator, let's say to the GPU, and which operating system which is shielded away from the operating system, but they don't exist. OS has full access to GPU. So there are some other ways which have emerged. There is a concept of neural networks which are operating over encrypted data. So that way I can run the neural network on the GPU and yet sort of work over encrypted data. So that's one possibility. Another possibility is to have some special GPU which actually have some sort of which can essentially create a encrypted tunnel into your enclave. So there are some papers out there now which talk about how to securely execute machine learning algorithms and all in this manner inside trusted enclaves. Okay, so moving on, this whole issue of sort of providing hardware assist which can help you store information in a secure manner against prying eyes is not exactly a new thing. What is new is the approaches which have been taken. So there are other purposes because of which you may want to have secure information into the device, which at a later point in time you might want to query and verify that the device has not been tampered with. So for example, I deploy a whole bunch of sensor nodes out there, and I want to make sure that someone doesn't go and replace them with a replica with their own firmware or things like with manipulated firmware, things like that. So before these TPMs and SGXs, well, not SGX doesn't play that role, but the TPMs and like the Apple version of the secure enclave and all, more common traditional approach which has existed historically is to put these things in a tamper-proof package. So that's a physical approach to creating such things. So basically the idea is that you would have a secure processor, so to say, which has the secrets in it. So let's say the keys that you write into the flash memory at the time of manufacturing, and then you put it inside a tamper-proof package, and then usually these tamper-proof packages would have sensors, so that if any attempt to tamper them would result in destruction or whatever, some sort of notification. The problem is a couple of things. Firstly, all this fancy packaging costs money, and the second thing is that something needs to keep those sensors powered up. So even though the system may be powered down, you still want to make sure that the package, that part, the tamper-proof part, is still powered up. But this was done obviously quite a bit for sensitive things like military applications and all, for example. So this photo is one of IBM product, which basically the crypto processor which would plug into their PCs or servers or class products would basically be tamper-proof, protected in this manner. But TPMs and all essentially now at the silicon level, at the time you are making the chip, allow you to embed secrets into the chip in some manner. So how do you think you can put secret into a processor, a chip? Like, how would you do it in terms of design implementation? Like, how would you, let's say I want to,
Flash memory.
but when would you do it? So, okay, fine, I create a flash memory on my chip, but at the time of fabrication, every processor has a flash memory, okay, and yet I want to put a unique something in each one of them.
Before you put it in the motherboard or something, you first turn the diffuser on.
Okay, so you could do that as a board vendor. You can put stuff there and maintain a database where you say, I burnt this one into this, right? That still doesn't fully solve the problem. Now imagine if someone is able to read the content of that flash, right, then they can just create a replica. So now suddenly you have two nodes which are offering the same secret identity. So that didn't quite solve the problem, but the bigger issue is it's also non-scalable, right? I mean, what is happening is that every device you are manufacturing, you are having to put in this kind of extra effort. There are other ways they do it, like for example, one is they may have a set of wires on the chip, and then using a laser they can cut some wires. Okay, so you can basically almost like etch in after the manufacturing kind of the final step, you can do something. But those are the kind of things which would happen out here. Like, I mean, a product like this, of course, the keys were burnt in by IBM and then put into the tamper-proof package, and of course, IBM would have this kind of information someplace. Okay, so you could, but there are hopefully there could be a better way for doing something like this, right? One that is more scalable and which also prevents easy duplication and all also. Particularly places where tamper-proof packaging is not easy to have, okay, I mean, which is often the case. So that some years ago, I would say at this point maybe a decade or so, I would imagine, is this concept emerged called physically unclonable functions. Okay, and the idea is that we are going to now extract the key from the physical system itself by making use of the unique characteristics of the physical system which are inherent in the physical system. So specifically, the idea would be, think of puff as a piece of hardware where I give it a challenge and it gives me a response. And so it's very easy. So I'm basically going to test the system by giving it a challenge and have it run through this puff to give me a response, and I'm going to check whether the response matches what I was expecting. But I want some characteristics out of such a thing. So first thing is, it should be easy to evaluate, and so it's fast. Okay. Secondly, it should be very hard to reproduce it. In other words, it should not be possible for me to create two puffs which have the same challenge response function, right? So think of challenge response as essentially some sort of truth table, right? Like, challenge is the input side, response is the output side. So we want to make sure that it is very hard to reproduce. It looks random, so shouldn't have the predictability. So obviously, if I can easily compute the random response from the challenge, then the purpose gets defeated. So it should look like a random function, and it should be unpredictable, even if adversary has physical access to it. It can manipulate the power supply and stuff like that, and it should still have this property. So the idea then is that if I were to have such a magical circuit, I can put it inside my TPM and then make use of it for all the crypto stuff and all, right? I mean, once I have this, this is basically a truly random function. Basically, that's what we're creating. So the question is there a way I can achieve this thing without going through what you were saying, burning in a challenge response curve? Okay. So more formally, then you can think of a set of requirements that this puff should have. So if I sort of they are random functions. So one of the ways you can say is that if I give the same response to, let's say I made 10 chips in a batch, okay, I give the same challenge to the 10 chips in the batch, their output should be wildly different. It should not be that they just differ by in a predictable manner. Otherwise, again, I can make use of manufacturing information and all and have some predictability. For a single puff, if I offer the same challenge today and a challenge today and the same challenge tomorrow, I should get back basically a response which is identical or at least very close, so that I can use standard sort of closeness metrics to kind of detect that. So in particular, what it means is that noise, aging, temperature, all these kind of things, they should not perturb things much, right? It should roughly be the same. And moreover, there should be a huge amount of unpredictability in this manner, which is the space of should be large enough, the uncertainty should be large enough, so that I can't if the space of if the entropy in the response to a given challenge is tiny, then again wherever I'm using it, I can basically use it for I can basically do brute force search to kind of break into this thing. So essentially sufficient entropy in the output. So conceptually those are the requirements, and kind of the interest has been, can I create these puffs cheaply, okay, in standard things that my systems have, and one of the things obviously are the chips themselves. So but there are other ones. I mean, like for example, people have explored puffs using other aspects of systems, like if you look at sensors in your cameras, okay, and you put it into a totally dark scene, okay, so put the lens cap on, and then you look at the image, it's not perfectly black, it has all this kind of noise there, right? And actually it turns out that that noise pattern is pretty unique to the sensor, in the sense that it's almost like a fingerprint of your sensor. So people have attempted to use that as a puff of sorts. Another one is scratches on lenses, micro scratches on lenses, okay, they naturally exist and you could use those. Noise in radio receivers, drifts and clocks, it turns out that a lot of these things have, or noise in inertial sensors when they are stationary, a lot of these things actually people have attempted to use as puffs, although just because they seem random doesn't mean they are random necessarily. So a lot of these things get proposed and then get broken down. Some of the examples I'm going to cite about puffs actually have been broken since they were proposed. So there's a constant tussle between these, because we are one of the difficulties about relying on physical phenomenon is that we kind of go on faith that it is random, okay, but in reality there may be some predictability because of manufacturing and whatnot that does exist. A lot of work on puffs happened here at UCLA. Professor Mihrak Potkonyak and CS, they did a lot of work in this space, and also Puneet Gupta in ECE, his group has been making use of specific semiconductor manufacturing characteristics to sort of create puffs. So the basic idea when it comes to puffs on silicon is to exploit the fact that there is variation in semiconductor manufacturing processes. So as you know, these chips are made by putting down the same geometric circuit on different parts of a big wafer, and then of course you make multiple such wafers. So there are variations over the space of the wafers, or the like a chip on one side and a chip on the other places on the same wafer would be different, even though nominally they are the same geometry that you are making. And then there is wafer to wafer differences that occur. So so this process variation is something that circuit people normally think of it as evil, because it means that there's a lack of predictability. You make 10 processors and their maximum frequency may be substantively different, their power consumption may differ, and so on and so forth. but so no two ICs are identical, but for our purposes, actually that can be beneficial. If harnessed correctly, maybe you can create a puff out of it. So, for example, you have made two chips. They have the same circuit, but you measure the delay between 2 points in, let's say, some combinational circuit, and you measure delay between input and output. The delay characteristic, assuming same voltage, same temperature, and whatnot, the delay would be different. Okay, between otherwise identical chips. So. So the idea is that I can somehow, crudely speaking, like let's imagine that I offer the challenge to this combinatorial circuit, and then I measure the delay between an edge here and the edge out here, and that delay is the response. And because this combinatorial circuit differs in its characteristic across instances of the chip, then the challenge to delay at mapping is different, and if it has sufficient separation, then I can use it as and unpredictability, then I can use it as a buffer. So that's a loose example, but let's see how sort of this works out. So an early silicon puff worked the following way. So essentially, it takes a lot of latches. Those NAND gates with back-to-back structure, or NOR gates with back-to-back structure, and you kind of create a cascade of them, and so like large number of them. And the idea is that each challenge basically creates kind of two paths to the circuit. Okay. Actually, they will not be latches; they would be simply feed-forward circuits. But the idea is that depending on if this bit is 1 versus 0, you basically will either take top path and bottom path, or they will shuffle. So it's a what is it? It's a conditional shuffler. Okay, I mean if the input is 1, it doesn't shuffle. If the input is 0, it shuffles. Let's say. Okay, so my challenge is really whether I'm shuffling or not shuffling. Okay, so I have 2 to the power n possible paths that exist in this system depending upon the n number of bits of challenge. And then the idea is that different implementation, different chips with the same circuit, the delays on these things are all going to vary because of that variation I referred to. And therefore, for a given challenge, whether I get the delay, whether the input to the delay here or the delay here is which one is larger or smaller will depend upon the chip. And then I use an arbiter circuit. So, what does an arbiter circuit do? It basically declares a winner. So all this arbiter stuff is doing is basically saying if the top edge comes first, maybe I'll go 1. If the bottom edge comes first, then I'll go 0. So essentially, you throw a challenge, and then it will tell you 1 or 0, depending upon, for that particular path, whether input to top was faster or input to bottom was faster. Okay, and then what you do is you do this thing for a whole bunch of circuits. So, like on the chip, maybe you can have, let's say, 20 of them. So now you will basically get a 20-bit response out there for a particular challenge. So you basically, and you can make things arbitrarily in your favor by increasing the number of circuits, number of parallel circuits that you have. So essentially, kind of a bigger, larger number of bits of the response. So each challenge, so digital response is based upon, again, the delay between the rising edge and the input, and the rising edge on the top and the rising edge on the bottom. And we're going to select that bit of the response is going to be 1 or 0, depending upon who wins. It turns out that the path delays in this fashion are nicely distributed. There is a lot of sort of stochastic variations across them, simply because of manufacturing variation, right? I mean, different chips, and then if I have multiple of these on the same circuit, then again, if I take 2 of these circuits you would see, and provide there's a rising edge at the input at exactly the same time, and let's say all the measurements in my design were the same, you would still see the two to be to have a randomness between them. And so you just take a bank of these. So so that's kind of the story. Now there are obviously issues in this. So firstly, one issue is that noise. So the thing is the following: I take the same thing and same circuit and try it repeatedly, okay, for the same challenge, and you'll probably see some perturbations between them, partly because of temperature and whatnot, the path delays were not changing. Maybe they were too close, so tiny perturbations. What else do you think can affect this thing? So firstly, what can change over time to affect? So temperature is one. What else? What else affects the performance of our hardware circuit? Over time, what?
Like transistor level channel might be affected, so that will affect the gates.
Well, okay, so over time aging happens, and therefore the circuit characteristics change. Okay, so that's one. Okay, what about, let's say, same at the present point in time on a more rapid time scale? What else can affect the delays?
The time that it takes for the carriers to travel. Time that it takes for the carriers to travel.
No. Why would that change? I'm asking what can cause changes to happen? Voltage, right? I mean, a glitch of voltage, for example, right? I mean, that would be another factor that can affect things. So, so the thing is the following: there is a natural amount of noise that exists in this thing, right? Some perturbations will happen for the same chip. So it's not as if I'm giving it a challenge, it just literally gives me the same response every time. There's going to be some spread around that. And yet, I also want to make sure that when I give a challenge to one chip and a challenge to a notionally identical chip, they are far apart, right? So it's essentially some sort of a clustering thing, right? I mean, I want there's a cluster of responses around a challenge to a given chip, but I want this cluster to be quite distinct from the cluster corresponding to a different chip and yet another chip, and so forth. So it's kind of like a you have to be careful from both directions. So this is like I said, this was one of the very first puffs that was proposed. It's been since broken using machine learning methods, but leave that aside. The way this thing was approached was, I mean, as you can see that the process is quite old, 0.18 micron, that's 180 nanometers. Right now we are in what? Anyone? Huh? How much? 8 or 7, or I think even 4. Yeah, so we are there. So this is like probably 5 or 6 generations away there. Okay. Variations, by the way, become worse as we have been shrinking the devices. Can you think of some simple reason why variations become worse as geometries go down? Like, why would variation on a say 14 nanometer chip be worse than on a 180 nanometer chip? Well, remember here we are kind of dealing more with the geometry. Basically, you kind of head in the right direction. I mean, basically, you are dealing with fewer and fewer atoms in the same for the same transistor, right? So if I have a placement, if an error of placement of one atom this way or the other, when I am doing the fabrication, the impact is a lot more. So if you see the amount of variability that exists in performance of devices, it has been increasing. So while obviously the performance has been improving, but that improvement in performance is associated with a larger variance in that performance. But going back out here, so what they have is the following. they basically firstly show that things are tightly controlled. So the red part here basically shows measurement noise for a chip X. So at a given condition, they throw the same challenge at chip X and they measure how much the spread in the response was. So this is showing kind of the noise which is occurring at an instant in time for that particular instance. Green is showing that how resilient it is if I change the ambient condition. So this was at one temperature, the green one is at a different temperature. Okay, so how much worse off we are? There is more unpredictability, and you probably want that within the operating regime of your hardware there is sufficient compactness. But then at the same time, what you also want is that the response of your chip X and a chip Y should be sufficiently far apart. So what they are showing is that the measurement from the same chip at the same instant time roughly have a half a bit difference. Measurements from the same chip across a range of temperatures roughly a 2-bit difference. So you're losing 2 bits of your response just to this noise. Distance between chip X and Y is 24 bits. That's really what you are kind of playing. So that was then under this example, but the idea is that essentially I can verify if I have 100 bits of response, so 100 such circuits that I had shown, then I effectively get a 24-bit distance between two random chips there, and sufficient to identify a fairly large number of chips. That's kind of the idea. Of course, you can amplify it more by just having, instead of 100, maybe have 1,000 of those circuits, and those are still tiny circuits, so you can put them in a corner of your chip and be done with it. Okay. Now, the questions. So it seems like at least there is good properties in a system like this, in an approach like this. Then could we make sure that it is resilient against an adversary? So one question you can ask is, let's say the adversary has the chip. You deployed this thing, it's able to do what is called as a chosen plain text kind of thing, or in this case, it can query it many times. Give a challenge, get a response. Give a challenge, get a response. Okay, let's say it's able to do that. Can it then construct a software clone of this thing? Okay, in fact, can it construct a software clone by maybe opening up the chip and examining things and all, right? These are all kind of things that you'll have to worry about. Can it recreate a clone, either a hardware clone or a software clone, to essentially bypass your mechanism? So the intuition in the original paper was that it won't be possible. I mean, even if you look at these wires and all, create an exact physical replica is super hard. Just the measurement there itself is going to create a lot of noise, and that the space is too large, so that modest amount of querying is not going to let you invert this function, learn this function. These kind of assumptions, just because something is large and therefore a modest number of queries will not do it, are often made, I think foolishly so at times, but let's say they are made. So that was kind of the idea, that this is a good puff because it's physically hard to recreate and it software wise is hard to recreate. That was the assertion. It turns out that many years later, it was broken. Okay, so essentially there is sufficient predictability, it turns out, and with some other knowledge of how these systems work and all that you bring, what they thought was what they thought was sufficient distance, actually the distances were much tinier, and therefore one could, by sufficient number of querying, one could break it. So the hunt for a good puff, obviously, started something like this. This was cool way that they went around doing it, but of course the specific mechanism got broken. There are other ways of making puffs, and essentially it boils down to other ways of either exploiting randomness that is already there in the hardware or introducing randomness at the time of manufacturing somehow. So putting in materials and stuff like that, or exploiting, like if your circuit has DRAM or SRAM. I think last time one of you said that the starting state of I think you had mentioned that, right? Yeah, the starting state of memory is random, so people have tried to exploit that idea also. So what are SRAM circuits? I mean, SRAM circuits are basically, again, the starting state, depending upon the sizes, would be 0 or 1 because they're essentially symmetric circuits. Some of these assertions, the DRAM one, like I said, has some predictability on the prior state, so not quite. Magnetic effects, photonic effects, vias. Vias are those connections between different metal layers on chips, thickness of metal varying in these things. So all sort of stuff which normally exists on the hardware side could potentially be exploited for this purpose. So this is the idea behind an SRAM puff. So SRAMs, this part, these 6 transistors, is what a SRAM cell looks like, and then you take the left side, right side, feed it. Essentially, it's the SRAM circuit. So after power up, it would depend upon subtle manufacturing things, and people showed that with these, at least, there is a consistency in terms of the state that they start out in. So when you kind of come up with the SRAM and you examine the content, then there is kind of a signature present there. DRAMs has some more of a persistence there to it. Okay, you can also find, since SRAMs exist on FPGAs also, so having a puff on an FPGA is also kind of possible. So yeah, this is some examples showing that there is a spread for the same chip, and then you have separation among different chips. Okay, so physical attacks on puffs. So there are you're not limited. So thus far, kind of the notion of attack was, can I do it if I'm at the liberty of like just querying and all? But what about an adversary which is able to physically attack the chip in some manner, like for example, manipulate its voltage or things like that? So one thing is that you could design packaging and all such that removing the packaging, for example, would result in the puff getting impacted in some manner. So there are protections that you could do against it, but this does remain a challenge that adversaries who are particularly well equipped can measure things on die also, and also on the chip. They can remove the top of the packaging and then kind of examine the wire traces and all. So those are issues as well one has to worry about. So the hunt for whatever good puff goes on. There are papers and funding from the defense agencies and all towards sort of creating these things. Okay, so if I could create puffs, then essentially I can use the puff as a unclonable key, which is unique and which only the chip knows, right? I mean, it's interior to the chip. It's not something we deliberately put, unlike the earlier suggestion of burning in a random number. Here, no one knows what it is, right? I mean, there is a built-in puff. We know it exists, but we don't know what it is precisely because we can't recreate it. So you can almost say that we are essentially, I mean, one way of you can think about the puff is that it's a database of challenge response pairs which is being burnt in at time of manufacturing, and no one knows other than that hardware as to what that database is. And so the idea is that once you have this capability built in, then you can use it to do all sort of interesting, useful crypto things on top of it, generate random keys, stuff like that, generate public-private key pairs, and so on and so forth. So there are a variety of ways it is done. Again, very importantly, these puffs are now used in TPMs, and also so essentially to reduce that cost burden, like no one has to burn it and all. So TPMs, which are made by many of the manufacturers now, ST Microelectronics is one of the manufacturers of these TPMs, so they use puff pens in recent years. So and then in turn, on top of it, everything that TPM enables basically gets enabled. So puff is kind of that enabling technology underlying that. I think I'm going to skip these slides. Yeah. Those are just different usage scenarios. Okay, so summary of puffs. Puffs are basically providing this built-in secret, unique to a chip, and you can learn some select input-output behaviors, but no one knows the full characterization other than the hardware itself. Kind of the risky part out here is that the faith in these things is often built on top of physics, which we may not fully understand, and therefore many a times these things have been subsequently broken. So you will not find like a mathematical proof that a given approach to puff satisfies all those requirements that I laid out earlier. So there is still an element of faith, and which is why what people have tried to do is they try to show that, I'll do some number of challenge response, feed them into a neural network or something like that nowadays, and then let's see whether I have achieved some predictability. And it turned out that given at least sufficient amount of data, they are able to kind of break it in many cases, and so that's why kind of the hunt goes on. So you might want to think about like what are the other sources of randomness that exist in the systems. I kind of pointed to some, and there may, in any given system, there might be other things, but it has to satisfy those properties, right? I mean, it has to give me a consistent result across time and across environmental conditions for a given instance, and yet it should have sufficient randomness of responses across different instances, right? And finally should be unpredictable. I mean, that goes without saying. So those are often sort of hard to meet entirely simultaneously, so which is why it kind of remains interesting. So there are conferences which focus on hardware aspects of security, and puff related papers are still sort of quite common there because people try to come up with creative ways of coming up with puffs. Any questions before okay, so puffs are basically a building block, not just I mean, if you kind of step back and think about it, puffs in part are providing randomness and all that we can use for keys, but puffs are also providing sort of this unique identity of sorts, right? I mean, one which is non-clonable and all, right? I mean, I can kind of verify. This leads to kind of a broader problem, which is I am in a remote, I have a bunch of remote devices, and these devices could potentially be physically manipulated. How do I make sure I can trust it? How can I make sure that the remote party has not been manipulated in any shape and form? So just to give you how do we do it in some of these systems, right? How does your bank know that a particular client is a valid client? So there we do it by password, right? I mean, when you log in, it kind of makes the assumption that everything is okay, I'm authenticating the user. But before that, let's say you also want to make sure that the app you are talking to is a valid app. It's not some fake app through which you are coming. Okay, so in that case, now what happens there? Well, what happens there is that Apple or Google kind of provide the necessary infrastructure to make sure that the server can trust that this request is coming from a valid, genuine client and not a fake one. But what about one level deeper? How do we know that it's a genuine phone or a genuine device or a genuine Raspberry Pi that you are talking to? So remote attestation basically refers to can I remotely attest that that piece of hardware and software in its totality is genuine. Okay, it has not been tampered with and all. So essentially, you have a bunch of sensors out there. You're getting these messages, whatever, with some readings, values, and timestamps and stuff like that. How do you know that it is actually coming from a genuine source? So the adversary could be some entity in the network, someone who has corrupted the software in, let's say, your access point or some network router, and is able to read, modify, falsify communication in some shape and form. Or your adversary could also be someone who has modified things out here, right? So somehow you want to provide assurance against these kind of adversaries who are able to modify things. So now let's imagine, so network adversaries are easy to, quote, take care of, because I can say I can use VPN or HTTPS to this is okay. So I can use a authenticated, integrity protected communication channel. So remember, authenticated and integrity protected we covered in the crypto lecture. We make use of digital certificates which are presented. We make use of the message authentication code, and of course the encryption part of it. Okay, but we still have the possibility that the firmware itself might have gotten compromised. So malware can extract secrets, can change the state in memory and whatnot. So it's a more dangerous kind of situation. So we saw Stuxnet out there. So the challenge then is that this malware, which has now taken over the end device, is now you can no longer trust it. So somehow you need to verify that there is no malware on the remote device which has permanently changed its state. Now there are kind of two possibilities out there. One is malware which has modified the firmware, and therefore even when the device boots up, it's actually not the device you were expecting to talk. And the other are malware where if you were to examine the boot image and all, it's perfectly fine. But when the system starts running, because it has some bug in it, then a remote hacker can now inject stuff into it and change the dynamic state, and now it's no longer valid. But if you were to simply examine at t equal to 0, what the firmware was, maybe you won't notice anything. So attestation is basically the basic idea is that either at some point in time, I basically want to make sure that the remote device, which we call as a prover, has not been tampered with, is in the state that I expected it to be, and it has to be kind of a rigorous proof. So that's the job of these attestation protocols, and in turn they depend upon some sort of measurement of something about this device, its hardware state, its software state of the software and all, which we are going to provide to the verifier. So for example, let's say if we want to make sure that the hardware is not being tampered with, that is, no one has plugged any sort of weird device and all, which is going to do something. So you could imagine that the measurement process in that case, and my software is otherwise okay. So some trusted part of the software out here could run through, probe all the memory addresses and all, and see what the response is, and that becomes the signature. And if there was ever some funny device added, then that will show up in the signature. If I'm worried about, let's say, the operating system having been compromised, then your bootloader can do some sort of hash over the operating system and then send it out and do it. Harder cases are when the compromise has happened later on, and now you are trying to do. So people kind of explore things like some sort of challenge response to see what I'm going to get. So various types of compromise and all, but the basic idea remains the same, that at some point in time I want to prove that the state of the system in its totality, software and hardware, is the same as what an untampered system would have had. So now this process of attestation itself presents a challenge, that you want to make sure that your attestation protocol itself doesn't get tampered with, right? So you want to make sure that when the evidence of authenticity is coming in, the adversary can't easily tamper with it. Okay, so there are lots of issues right here you can think, like for example, I should not be able to capture the evidence from some past run of this attestation process and just replay it. Okay, that will kind of defeat the purpose. So just think about it, right? I want to make sure that you are providing me attestation of the state of the remote device as it is now, and not simply that one which you had previously captured and are just replaying it back in response to whatever a previous request that had gone through. So it should represent the real current state of the system. So that's the authenticity and timeliness requirements. Okay, how do you think you might want to do it? So let's just think about it, right? You want to, as a server, you want to make sure that remote sensor is it's just sending. Let's say I have a measurement process there which can just enumerate all the devices and all. Okay, I want to make sure it's the one for now. Can you think of some way of doing it? Like ensure freshness, not be able to replay.
You can have your remote device hash its current state with the current time.
Okay, so where is the time coming from?
Into the remote device.
It can come from a real-time clock or from the entity.
But what if it pretends, remember the software has been compromised, so it can put in any time. You heard something? No? Okay, see, like the obvious solutions out here fall apart, right? And okay, so firstly, if you go back to when we were doing the secure ranging and all, there has to be something which has to be coming from the querier side, right? Because otherwise, if you are solely relying on the party, it would be guessable, right? So I have to send either I have to send something, or remember there we were relying on some sort of a commitment kind of thing. But there has to be something which the server or I guess querier verifier is kind of providing, okay, which we need to bring in. It could be that it commits to a state, for example, and then I send it kind of something random, and then I ask for a function over it. I'll let you guys think about it, but it's kind of it's not that straightforward, some of these things, okay? But the simple things don't work, okay? Now, TPMs do help in this process. So part of the reason TPMs were created were to help with this problem of attestation. So what TPMs do is they kind of TPMs have an advantage, right? TPMs have an advantage that what can the adversary not do to TPM?
They're gonna modify
they cannot modify it, right? So TPMs come with some secret, perhaps the puff, for example, but adversary, but it's a root of trust. So adversary can mess with the firmware and all, plug-in devices and all, but TPM it can't mess with. Okay, so the idea is that TPMs play a role where they engage in this process of measurement and signing and then sending out things. So TPM based attestation is one. They maintain configuration information. They have specific sort of registers for it, and with the nice property that they can not be overwritten by software, they can only be extended. Okay, so essentially we prevent the operating system, or in this case the compromised firmware, to essentially erase the configuration state. It can only kind of append to it and all. So those are kind of the building blocks to then creating an attestation thing. So TPMs have these configuration registers where basically what you do is that you run through sort of this measurement process, and then you take a hash over it. So essentially you can imagine kind of by result in, I don't know, let's say a JSON file capturing the configuration, you sort of take a hash over it, and that's what you're going to put it. But still that begs another question, that how do I make sure that the measurement process itself has not been compromised with? So again, turns out TPMs take care of it. Once you have that, then the second part is, so now you have kind of, with the help of TPM, you have this securely measured the state of the hardware and the state of any firmware in there, and then you engage in an attestation protocol where you are going to basically verify prove to the verifier that things are correct. So in this case, again, there is kind of this protocol involving where there is a challenge set, and then the response comes back, and in this response somehow obviously it will depend upon the challenge together with that secure state you had made. Okay, so it's not simply measure and send it out, but rather in response to a particular challenge. So TPM based attestation plays an important role, but then we end up with the situation that we have lots of IoT devices which have no TPMs, and all these Arduinos and stuff like that and all. Okay, so no TPM is there. Part of the reason no TPM is there is because excuse me, these things are much more price sensitive. So TPM on a $500 PC is a different economic thing than on a $5 wireless sensing device, right? So TPMs are not as common in these, although some of this has begun to change, like I said, because the processors themselves now sometimes have built-in enclaves. There are software emulations of TPM that you would find. So if you Google for TPM and all, you'll see that there are some open source implementations of TPM thing, but they don't have the security properties that you're after. They are really meant more for debugging purposes and all. They are not replacements of genuine TPMs, because the genuine TPMs have this hardware support for maintaining secrecy. So TPMs cost, and of course there is also cost from the software side. You kind of put additional drivers and all. So TPM based attestation, while it works, has all these issues, right? I mean, it doesn't work for devices where we don't have TPMs. We have the cost issue, and then there is another issue which I kind of alluded to earlier. It only covers the initial loading of the software. So TPM attestation is only proving that you have loaded the right software. It doesn't deal with a subsequent compromise of that thing for a variety of reasons. It could be that the software was buggy and therefore some malicious input was given and affected the state, or software was fine, but maybe there was some intrusive side channel that existed, which let the adversary flip some bits and all, and that caused problems. So those things exist also. And also it deals with one prover, one verifier. The problem with IoT also is that many different parties may need to verify a device, and many different, and a given verifier has to work with a lot of IoT devices. So if you think of like a large-scale IoT deployment, you may have many sensors, and they publish data, and they may go through some sort of a broker or gateway and whatnot, and then their clients include many actuators. Like for example, the motion sensor may control the light, may control the lock, may control the security alarm, right? I mean, say, and each one of these parties, they have to somehow verify that are they talking to the right thing, right? So it's kind of a multi-party kind of a situation out here, as opposed to one verifier one. So many verifiers, many clients, right, who are trying to prove. So it's a more complex situation than kind of the TPS scenario. So, excuse me. Another issue is that one has to make sure that whatever measurements you are doing, they are resilient, or they take into account things like software updates. And all software is not a static thing; it gets patched. There is also the issue that even with these embedded devices, sometimes we plug in things. Okay, so the system configuration changes. So there are all these nuisances which kind of kick in, which also one has to sort of make sure one takes into account. So a lot of interest in recent few years has been on this issue of how can we attest and then all the things that built on top of attestation in these IoT kind of scenarios where you have sort of all those issues that I mentioned are taking place. So there are software-based attestation schemes. There are those obviously which rely on hardware in some cases, if the hardware is available, doing things at runtime, which is not just the initial load, but after it has happened. So a lot of interesting work which exploits different signatures that may exist in the system for this purpose. So software-based attestation, the idea out here is that there is no hardware feature to support attestation. So there is no TPM, so no secrets of any form that you can rely on. And moreover, you cannot guarantee that there is a specific code being run. Remember, you should not assume that the code which is taking the, as a verifier, you cannot assume that the code on prover is correct, because the code which is attempting to prove itself is compromised and malicious potentially. So on the embedded device, you have application code and all, and let's say you had put your verification code there. But all of this is, if this is compromised, then you can't rely on all of this. So how would we do it, right? I mean, you can't simply say, okay, I'm just going to take some sort of a hash over this thing by itself and just send it out, because the adversary, what they could have done is to basically take the hash and then put in their own firmware, and then whenever you ask, they just send it out. So that doesn't work. So what this protocol is showing is that how we can address this. This is again where the challenge concept is very important. So instead of simply relying on the prover provided hash of this thing, we really first send it a challenge, and then we require a hash over that and the nonce, the random number we are setting, right? So in this case, even if it had stored my prior transactions and whatnot, it cannot provide me this, right? Because it didn't know N1 coming in, so it doesn't know. And remember, we are going to use a secure hash out there, not your standard hash function. So this is an example where, without assuming anything on this side, I can, by software means alone, can rely on, can get something about confidence in that the state has not been tampered with. Okay. Okay. Some of the issues out here is that you also have to worry about runtime efficiencies, and also those things come up. Okay. Yeah, I think I can skip this. Then there are schemes which are which instead of relying entirely on software, they rely on kind of some minimal hardware support, which you can assume can exist. So, for example, there are things you can imagine where there is some tiny amount of code that may exist on the processor, or which cannot be tampered with post manufacturing. So a lot of microcontrollers you buy, they come with kind of an initial boot code, and in fact, if you are a large volume vendor, large volume customer for a manufacturer, they would be happy to put your own code. So it's lit on the chip, burnt in, can't be changed. So including, therefore, by definition, non-tamperable. So this would be kind of the very initial code which is up and running. Maybe you can have some key, kind of a unique ID which the processor comes in. So again, okay, and another thing is atomicity of execution of verification code. So the idea would be that, let's imagine that your microcontroller comes with this verification code, and let's also imagine that when we execute that verification code, no one can interrupt it. So I give it an input, it executes, and it gives me an output, and it is entirely non-interruptible. So even if rest of the code base has been compromised, I can't manipulate the intermediate results in any form. So turns out with certain properties like these, you can create much more efficient ways of doing some of this attestation and all. You could even begin to build some runtime strategies around this. So the schemes that I have described, thus far they're only still doing the initial check. Maybe at some one thing you might want to do is, for example, at runtime you might want to verify, are the data structures, is the state of the stack, are all of these things okay also? So you can begin to build things up. So people talk a lot about that, can I create on the cheap IoT devices where without any significant manufacturing cost, I can have some of these properties that we are talking about. So that's hybrid attestation. The only issue is that it does need some support from the processors, but for example, I mentioned that trust zone is now available on ARM Cortex M series things, so some of these things we are beginning to see on even tinier microcontrollers. Then there is the issue of scalability. So I mentioned that, but essentially what happens is that this model where you can say that there are many provers and often many verifiers. So imagine, like, for example, I don't know, let's take an example, traffic kind of a situation where maybe certain vehicles, like let's say ambulances, have special privileges that they can ask the traffic system to give them right of way or something like that. Okay, so in these kind of settings, you might there are many verifiers along the way, right? I mean, every traffic intersection is in such a mode, right? So as it is crossing through, it is repeatedly kind of verifying itself, and likewise there are many provers because there might be many such vehicles in the thing. So so this issue of creating attestation where you have end-to-end scenarios, or whatever, end-to-end scenarios, and you can kind of work across them. So the challenges that are faced is that this presents additional issues like, how do you kick someone out? So for example, it turns out that currently for roadside communication between vehicles and roadside things, the protocol they use, where let's say at some stage you decide that this vehicle is no longer allowed to access those resources, it takes them a long period of time to kick them out. So one of the challenges also is once you know that the device has been compromised, you want to also kind of revoke it out. It should not be there. But if the verifier was centralized, it would have been easy to do. But if the verifiers, there are tons of them, then I may know that this is no longer valid client, okay, but the others may not know that. So dynamic membership, dynamic topology, all these kind of considerations which come up. So let's see. Yeah, so that's more of a portion. The final one is this whole issue of runtime attestation. So it's not simply that I'm attesting what is happening at t equal to 0 or upon boot up, but subsequent to that. So traditional attestation measures binaries and hardware configuration at the initial load time, but runtime attacks are a huge problem. So runtime attacks will see them in that recorded lecture that I talked about that we'll be offering. But runtime attacks, loosely speaking, exploit ability to inject inputs that then cause the program state to get corrupted and then have the program do something that you didn't want it to do. So you'll see more about how to be done, and there's some very cool attack ideas and all people have explored. There's a concept called return-oriented programming that some faculty at UC San Diego had come up with, where kind of essentially at this point, if you want to be evil and if the software has a bug which allows these kind of things, they're very sophisticated tools where you don't really need to know a lot of gory details under the hood. You write whatever bad stuff you want to do after penetrating, and there are compilers and whatnot which will help you design the malware payload to do it. So attack side is pretty far advanced. So what happens now is that the runtime state has been compromised. So how can we check for the runtime state? Well, so now essentially what we have to do is, while the system is running, I'm going to send some sort of a request and ask it to generate a response, and again I'm going to verify that. So that's a fun approach. The issue out here is one has to be careful that it should not be very burdensome, right? Because this is while the system is running. Another possibility is I can monitor the system externally and make sure it is okay. So one approach for the latter is something that we saw earlier, which is the side channel thing. So there, when we looked at the lecture, we were looking at as an attacker, which is trying to extract information. But you can also imagine that the side channel signatures of a device are a signature of its validity. So if a device has been compromised, like for example, let's say now it has begun to send packets to some server in some nefarious country. Okay, so now there is some external additional stuff it is doing. Well, if we do our job right, that change will manifest in the power signature or in the RF spectrum or something else. So by monitoring the physical emission from the device, I can make sure that it has not been tampered with. This is very similar to, for example, what network managers do, where if a machine has been attacked, then the traffic from that machine will show some anomaly. So this thing falls under the area of what is called an anomaly detection, where there is a normal pattern of something, traffic, power measurement, sound, light, whatnot, and then there is some abnormal stuff. And kind of the idea is you train some sort of a classifier over lots of data and then show that it obeys. And the other approach is the one which I'm showing out here, which is embedded in the device. There is some sort of function which helps in the proving part, and at runtime the verifier will throw some sort of a challenge at it, and then it has to respond to make sure that the state is good. It sounds easy, but as you might imagine, it's very complicated because the state of the device depends upon the inputs it has seen and all, right? So the code may be the same, but imagine the state of the stack, state of the heap, linked list, all the data structures in it and all. They still have to, they can vary highly between genuine devices, nothing tampered with, and yet we are trying to detect tampering. So, but anyway, that's kind of the idea, that we try to detect. I'm going to skip this. But we basically have the code prove that it is correct by throwing a challenge at it and it generating a response, and that designing it in a manner where the response would be resilient. So runtime attestation again faces a lot of these issues that performance and all that come up. There are I think probably the coolest stuff that I've seen is the one I was describing, where using external measurements we kind of try to see that nothing has been tampered with. So at this stage, by monitoring RF emissions and all, some of the work is suggesting that even tiny perturbations we can do. So essentially the way those work, and I think the very first paper on Tuesday deals with that issue, which is let's say I have some program, some sensing program and all, it has a loop, and even one instruction change in it, we can detect its effect on the RF emission or the power consumption and all, and then kind of indicate, something has gone wrong. So a lot of effort towards runtime attestation that goes on. Some amount of hardware assist can certainly help quite a bit. There are other things, like you can imagine if at the board level you could have some entity sitting, and it can sweep through the memory and do some sort of analysis over it. So for example, does everyone know what a JTAG port is? What does it do? What does it allow us to do?
Programs,
Okay, you can download programs. What else?
debug.
How does it do debugging?
Separate
Sets breakpoints at the board.
Now, what happens over the JTAG port? Like what exactly? So if you think about it, for JTAG to do debugging, it has to be able to examine the registers, and it has to be able to examine the state of the memory, right? So I can use the same facility. So I can have literally kind of some element on my board which can use the JTAG port to stall the processor at some point and examine, and then make sure it's all okay, right? So you can use that port. Okay, so that's one approach. Another possibility is that if your processor is something which allows direct memory access, everyone knows what DMA is, right? DMA allows you to not just the CPU but some other I/O devices to access. So again, you can imagine that this verifier can run in the background, make use of the DMA, sweep through the memory, do some sort of aggregation over the content of the memory, and again verify, right? So there are all these other ways if the board was under your control, right? I mean, you could design these things in. If the board was not under your control, you can attempt to do some of the software things which I kind of skipped over, or you could do this side channel sensing kind of things, right? So these are some of the approaches which are emerging. But the bigger problem basically is, I mean, hopefully you kind of appreciate the importance of it, right? I mean, you don't want to install this framework, your infrastructure, and then only to have it be tampered with. There are other types of tampering which can also happen. So someone can move your sensor. Let's say we went ahead and deployed sensors on the front door of your every home to protect against whatever burglary, and then someone comes and moves them to some other door. How would you protect against that? Any thoughts? So we installed our sensors, devices, and then someone comes and moves them. No change to software, they just move the thing.
It is the gateway device.
Hmm?
The gateway device. Like
Yeah, it can still talk to the gateway device. It's just been moved a little bit, so it can still communicate.
You just screw the stuff in place. I mean,
Uh,
that's the simplest thing.
okay. So you can make it physically hard. You can put an armed guard there and protect against. But what else do you think we can do?
You can hide the sensor.
Hmm?
You can hide the sensor. Like,
Okay, you can. Okay, so they are all good suggestions. You can hide. You can make it hard to move. Let's say.
You can put an accelerometer so you can see if it's
Yeah, great idea, right? I can put a inertial sensor of some form, so I can detect the movement, and if after installation it moved, I can just disable it immediately, right? Okay, so that's one. What else? Yeah, so actually, absolutely. So it's kind of in the same vein as your idea that is some sort of a sensor which detects movement. In fact, your home security sensors have this tamper detector. So whenever you unplug it, even for like replacing battery, immediately a tamper message goes out. In that case, it is a micro switch, and when you unplug it, that switch goes off, right? Okay, so I can detect displacement, okay, through these built-in sensors. Can you think of other ways of detecting movement? Excuse me.
using UWB.
How?
Measuring the receive signal strength. Across
Yeah,
the-
okay. So the idea is that can I create a signature of my context, right? So imagine that the device has some sensors, maybe acoustic, magnetic, radio signal strength and all, and then upon the initial installation and maybe after a few readings after that, it kind of takes a bunch of readings and constructs a signature. And then later on when it is moved, that signature will get perturbed, right? I mean, for example, if it was moved from indoor to outdoor, maybe it will see a different temperature profile or a different sound signature and whatnot. So essentially endowing the device with physical signature capability, which you can then build something on top of. So that idea has been used. In fact, there have been several attempts at using the context as a key of sorts also. That is only like for example, let's say a sensor claims the temperature is 25 at location XY. How do we know that the device is actually at location XY? Provably. So we kind of saw some attempts towards that in our earlier lectures. It says that it's XY at 2 p.m. on whatever, February 2nd. How do we know that the reading was actually taken at that time, right? So a lot of these things are also part of attestation, that can I attest the validity of everything. So that original slide I had earlier on in the slide deck, that little sensor measurement thing, each one of those things we need to be able to verify. One episode I was engaged in a project with some collaborators in India on mobile health, and one of the challenges they were facing was the following, that people would, so the issue there was the following, that they would send these medical workers to remote villages to collect readings, and they would get money based upon the readings they collected, okay, from the genuine patients. So guess what? The readings were not collected from genuine patients, but basically just random people. They didn't even visit the village, right? So now you want to verify that the reading is actually taken from that individual, right? I mean, so these are all part of the attestation problems, that it's a genuine sensor with the untampered hardware, untampered software, placed correctly, measurement was taken at the right location at the right time, and so on and so forth. So all those things go under the umbrella of attestation, and your challenges include adversaries. I mean, in our embedded context, adversaries which have physical access to the device, not permanently perhaps, although in some cases permanently too. I mean, I can tamper with, like right now, many insurance companies are handing out devices for your car because they do pricing based upon the movement of your car and all. So in that case, if you are the adversary, you have almost, you have 24/7 access to the device, okay? You want attestation which could be done truly end-to-end so that intermediaries cannot mess with it. And I guess the final thing is there are just gazillions of these devices of all types and all sort of temptations that exist to tamper with them. Another one I had heard was in Singapore, kind of money being given as part of competitions where if you walk more and all, then you get credit, okay, by the government. And again, I hand my device to someone else to kind of collect the data. Or another example, which I guess Swapnil mailed in my research group, some artist in Germany fooled Google's traffic. Some of you have read it, right? So he put 100 Android phones on a cart and just went around the city, and wherever he went, there was congestion reported on Google Maps. Okay, so these are all different phases of attestation that are happening in. Okay, so that's attestation of properties. I mean, those are genuine Android phones, but anyway, so I'm going to stop out here. On Tuesday, we are going to have the paper presentations.